Let's talk about the subatomic particles. Sub is a prefix meaning below. So below atomic size, subatomic particles. There are three major subatomic particles. There are others, but we'll leave those to the physicists. We're going to talk about protons, neutrons, and electrons. All atoms are composed of the same three subatomic particles. So protons and neutrons have nearly the same mass. Here's the mass of one proton, here's the mass of a neutron. They're both crazy small, 10 to the minus 27 kilograms. So 0, decimal point, 26 zeros, and then the number 1, kilograms. Really small. But look how similar these are. They're differing in the fourth decimal, or the fourth significant figure. So for most purposes, they are the same. The electron, though, is much smaller. This is 9 times 10 to the minus 31 kilograms. It's about 1,800 times smaller than the proton and the neutron. So if the proton was a baseball, the electron would have the mass of a grain of rice. And that's why, in terms of the mass of the atom, the electrons really don't contribute much. And for many purposes, we can just ignore their mass entirely. Any questions? You do not need to memorize these masses. Well, those numbers, these guys right here, these are awkwardly small numbers to deal with. And so what we generally do is, instead of using these large negative exponents, we're going to use a unit that is closer in size to what we're measuring. So the metric system has lots of prefixes, but this is the only situation where we need to go this tiny, and so there's not, I don't even know of a metric prefix that would be useful here. So they made up a unit. That sounds a little flip, doesn't it? Oh, they just made up a unit. What the heck? Where did any of the units come from? They were all made up. So they had a need for a new unit, so they created a new unit. It doesn't have a very clever name, but the name is descriptive. It's called the atomic mass unit. It's a unit for measuring atomic mass. And the abbreviation is AMU. That's not AMU, which might be a cousin of an emu. It's AMU. So here's the definition. 1 AMU is 1/12 the mass of a carbon atom that contains 6 protons and 6 neutrons. That's kind of a weird definition. Basically, what they're saying is, here we've got an atom, and in its nucleus, it has 12 of these larger particles, neutrons and protons. And so we're going to say that that atom weighs 12 atomic mass units. So then 1 atomic mass unit is 1/12 of that. They chose the carbon atom because it's very stable and it's easy to work with and it's accessible to everyone. So the result of that is the mass of a proton or a neutron is approximately 1 atomic mass unit. The charge of the proton and the charge on the electron are equal in magnitude but opposite in sign. So the proton's plus 1.60218 times 10 to the minus 19th coulombs, and the electron is that same number but opposite in sign. We're not going to use the charge on the coulomb much at all in the rest of the charge on an electron or proton in coulombs much at all. Chemists don't do a lot with coulombs. We give you the number there to show you that it's really, really small. For the most part, though, we deal in relative charges. The proton is +1, the electron is -1. In terms of masses, the proton is 1 atomic mass unit, the neutron is 1 atomic mass unit. And for most purposes, we can consider the electron to not have any mass at all. because it's like the bird on the semi-truck. Its mass just is not significant compared to the rest of it. Any questions? So when we're talking about elements, there's lots of different kinds of elements. And what makes one atom carbon and another atom nitrogen? What's the identifying characteristic? It's the number of protons that are in the nucleus. So the number of protons is a little bit like the soul of a person, right? You can change your outward appearance, or it could be changed for you by an accident or something. You can dress differently, you can act differently, but you are still you, no matter what you do. You can't change who you are. The number of protons defines what element an atom is. The number of protons doesn't change. There are neutrons in the atom, there are electrons in the atom, and those will change under certain circumstances, but it's the protons that define the element. So that's an important number, and we call it the atomic number. The atomic number is the number of protons, and is given the symbol Z. I think it should be A, but they didn't consult me, and they're calling it Z, so we have to go with that. So here we have a helium balloon. In the helium nucleus, there are 2 protons. Every helium atom has 2 protons in its nucleus. Here's the graphite in your pencil. That's carbon. Carbon has 6 protons. Every carbon atom has 6 protons. If you find an atom that has 6 protons, it's carbon.
That's the number on the top.
And that is the number on the top, on the periodic table. So here's a periodic table, and here's a blow-up of the square for beryllium. Above the chemical symbol is a whole number. That whole number is the atomic number, the number of protons. So we can look at the periodic table, and we know that beryllium has 4 protons in its nucleus. And in my class, you will always have access to a periodic table, something like this. We've got the one on the wall. For exams, I'll give you a paper copy. It's not necessarily going to have all the information on it that you might want, but it will be a periodic table. So, we can look at any element and tell, just from the periodic table, how many protons it has. This periodic table also gives the names, but the one I give you on an exam will not have the names of the elements on it. Each element has a name, of course, and a unique atomic number and a unique chemical symbol. And we just had a quiz on element symbols today. The symbol for an element is either a 1 or a 2-letter abbreviation that's listed on the periodic table. If there's the first letter is always capitalized. If there's a second letter, it is never capitalized. And yes, that's really, really important. So just as examples, helium is He, carbon is C, nitrogen is N. Now, some students like to write in all caps, and so they'll write helium like that. That's wrong. Yeah, I can tell you made the E smaller than the H, but this is a capital E. You can do that on all the rest of your paper, but do not do it on your chemical symbols. This is not okay. This needs to be He, lowercase e. We've kind of alluded to isotopes. And that was one of the issues we said that we had with Dalton's atomic theory. It said that all atoms of a given element are exactly the same. They have the same mass. And now we know that that's not quite true. All atoms of a given element have the same number of protons, but they can vary in their number of neutrons. So the example here is neon. All neon atoms contain 10 protons. We look at the periodic table, neon is element number 10 protons. But some neon atoms have 10 neutrons, some have 11, some have 12 neutrons. because of the difference in neutrons, the mass of each of those atoms will be slightly different, right? They'll be close, but be slightly different. So isotopes is the word that we use to describe atoms that have the same number of protons, but differing numbers of neutrons. Iso is a prefix that means the same. They're the same element, and yet they're different. I don't know what tope means. I should probably look that up. So most elements have isotopes. Not all of them do. This information about isotopes is stuff we're not going to find on the periodic table. The fact that neon has 3 isotopes, there's no clues on the periodic table that will tell us that information. That's been determined experimentally. And having 3 isotopes does not mean there's 1/3 of all neon is the one isotope, and another third is the middle one, and another third is the smaller. The percentages are going to vary with the element.
What exactly is an isotope again?
Isotopes, because you can't just have really a single. Isotopes is when you have atoms of the same element, they have different numbers of neutrons. They have the same number of protons, they have different numbers of neutrons. So they're all the same element, and yet there's these little differences. The relative amounts of each of those different isotopes in a naturally occurring sample is going to be roughly constant. So if you isolate carbon from some trees down the street, and you analyze the relative abundance of the different isotopes of carbon from those trees, and then you go to Russia and you get some carbon from there and you analyze it, the percentages of the different isotopes are going to be relatively constant. Not exactly the same, but pretty close. And those are called the natural abundances of the isotopes. So those are things that need to be determined experimentally. Advances in technology have allowed us to measure them more accurately, and understand that there are small but significant variations for many of the elements. We're not going to have to worry about that in Chem 1A, but there are variations. So we talked about atomic number, the number of protons. Another important number is the mass number. The mass number is the total number of neutrons plus protons in an atom, and that's given the symbol A. Atomic number. Atomic starts with the letter A. Wouldn't it make more sense if that was A, and this one could be Z or M or something? No. So we have to deal with it. Sometimes I help myself to remember things that seem backwards by kind of making a big point of how they're backwards. So we can symbolize isotopes in this way. This is called a nuclear symbol. Here, the capital X is standing in for the element's chemical symbol. And as a superscript to the left, we write the mass number, and a subscript to the left is the atomic number. So here are the symbols for the 3 isotopes of neon. They all have the same element symbol. They all have the same atomic number, but the mass number is different. The one thing I do like about how they did this is, so if we look at this neon 20 and we want to know, well, how many neutrons are in there? Well, we take the 20, subtract 10, and that gives us the number of neutrons. Because this number is neutrons plus protons, and this number is the protons. And when you subtract that, you end up with the number of neutrons. So it's the bigger number on top and the smaller number on the bottom. So neon 21 has 11 neutrons, and neon 22 has 12 neutrons. Another way to indicate the isotopes is to use either the chemical symbol or its name with a dash followed by the mass number. So we could call it Ne-20 or neon 20. The other symbol gives us the number of protons, which is nice, but do we really need to be told the number of protons in neon? We have a big old periodic table on the wall, and if we want to know that, we just look at neon, oh, 10. So this is an easier method. It's definitely easier when you go to type stuff into the computer. These symbols, those are a booger. You have to get out the equation editor to do those stacked superscripts, subscripts. And so we use these symbols a lot. So the symbol here, neon 20, or here's the nuclear symbol. And from this symbol, we can get the following information. The number of protons, see they're all the same. They all have 10 because they're all neon. The number of neutrons, and the mass number. All of this information is in the symbol. The natural abundance, though, is something that has to be determined experimentally. For neon 20 is 90.48%. Neon 21 is quite rare, 0.27% of all neon. And then neon 22 is 9.25%. And these percentages should add up to 100. Or very close. Yes?
Neon, the element itself, is that considered an isotope? Because we can have
Neon has 3 isotopes. There are 3 versions of neon. It's a little bit like you go and you buy a car. My husband, we bought him a Subaru Forester. Well, there's different models, right? And they cost a different amount of money, and they have different features. And yet, we would say they're the same car. It's still a Subaru Forester. But this one has the upgraded interior, and this one has a moonroof, and the other ones don't. So, but it's still a Forester. So, all 3 of these are neon because they have the same number of protons, but they're not exactly the same. Does that help? Sort of. These are 3 isotopes of the element neon. Yeah. Yes?
When we're dealing with whatever symbols that we use, they're not a single isotope, so everything we use, there's a little bit of each.
Yes. When we are dealing with elements, in most cases, and definitely when we work in lab, we are not dealing with a specific isotope of an element. We're dealing with the natural mixture of the elements. You can separate them, but it requires a great deal of effort, and most of the time there's no gain, there's no purpose in doing that. There are certain experiments where, yes, you want to have just the neon 20 and you don't want any of the rest of it. And you can separate those, but it's hard because they're so similar. So most of the time, we're dealing with this mixture of all the isotopes, and that mixture, where am I, is going to be this composition, whatever the natural abundance is. And whether we get it, from Fisher Scientific or you get it from the black market, it's going to have roughly the same percentage composition. That's a good point. Let's look at this. What are the atomic number, the mass number, and the symbol for the carbon isotope with 7 neutrons? Well, carbon, what's the atomic number for carbon? 6. We look at the periodic table, and conveniently there's one right here. Carbon is element number 6. That means the atomic number is 6, and the symbol for atomic number is Z. Z equals 6. What's the mass number for this isotope? The mass number is the protons plus the neutrons. So the mass number is A, and that's going to be the number of protons, which is 6, plus the number of neutrons, and they told us there's 7 neutrons. So that's 13. Okay with that? And then to make the symbol, we would put the element symbol, C, and we're going to put the mass number up here and the atomic number down there. That's one type of symbol. We could also call it C-13 or carbon 13.
And will the computer accept all of these when we use them?
It should accept them. It'll either be doing multiple choice or they'll be more specific. This is called a nuclear symbol, where you have the stacked ones. But all of these are perfectly acceptable names for carbon with 7 neutrons. Any questions? Another type of question we could ask is, how many protons and neutrons are present in an atom of this? Another problem with those symbols is, how do you read that? Well, I'd call that potassium 39. Well, how many protons? This number on the bottom tells us the number of protons. So 19 protons. And if we look on the periodic table and find the symbol K, it's 19, because potassium always has 19 protons. How many neutrons? Just subtract. 39 minus 19 is 20, so 20 neutrons. Any questions? So you need to know what these symbols mean, and given information in a periodic table, you need to be able to write the symbols. So I talked earlier about how atoms have no overall charge. And that's because we have the number of electrons being equal to the number of protons. But sometimes atoms will lose electrons or gain electrons. The number of protons won't change, but you can gain or lose electrons. And when that happens, then you do have an overall charge, and these are no longer called atoms, they're called ions. Ions are atoms that have a charge on them. They have a charge because they've gained or lost electrons. So a positively charged ion is called a cation. If you like cats, then that kind of makes sense, because cation, I have positive feelings about cats. If you don't like cats, you can say, well, Mrs. K has positive feelings about cats. We currently only have 2 cats. The negatively charged ions are called anions. And it's anion, not anion, which I guess might be like a funky onion. And this isn't cation, like a staycation or a vacation. It's cation.